printing, and also basically on design for local government, local authority approval. So I hope that you will enjoy our presentation. Myself, I'm going to talk about the state of the art, and then my other colleague will speak on design for 3D construction printing, and then the project team that it has to do with 3D concrete printing. As it stands today, 3D concrete printing is the fastest growing in the 3D printing technology. From available data, if you look at the slide that is presented here, from research data available, even though we cannot verify the source of the collection of the data, but all of these sources actually shows the same trend that 3D CP, that is 3D concrete printing construction, is the fastest when we talk about, growing 3D printing technology. If you look at the graph that you have here, the solid symbols here shows the actual and why the hollow actually shows the projected. So from 7% that you can see in 2022, projected to 9% of the 3D printing industry in 2030. But so if you look at it in terms of the compounded annual growth rate, we see that 3D concrete printing is larger when you compare it to other industry like aerospace and defense, automotive, healthcare, and the rest of that. Going forward, it is interesting to note that the market share or market studies of current and predicted global 3D concrete printing activity is quite interesting. Looking at the figure here, you will see that 3D concrete printing global market value reached 0.01% of the global construction in 2022. Again, the solid here are actual, and why the hollow symbols here at the projected value. It reached 0.01% of global construction in 2022, according to these reports that we have cited here. The green symbol that you can see, or the green symbols that you can see here, denotes projections that were made in 2018, 2020, and then 2022 to reach 0.5%. As you can see, to reach 0.5% by 2030, while the blue line are more recent projections up to 3.1% in 2034. So evidently, you can see if you compare the 2018 projection for 2024, it actually exceeded in 2020 and 2022 as well, almost by a factor of 10, which is quite significant. So we see that indeed 3D concrete printing technology is quite, gaining ground globally. And from this figure, we see that 3D concrete printing in terms of location spread around the world from one continent to the other. We'll see that the market expansion is actually driven by 3 continents: North America, Asia, and Europe. And then Africa is also coming behind with a total of about 130 buildings. This is a snapshot of 2023 statistics. And it is interesting that, especially as seen in North America, Asia, and Europe, a number of fantastic projects from school printed in Malawi up to some parts of Europe. My colleague Marchant is going to talk more on some of these projects, so I'm not going to belabor them at this time. To bridges and housing, different sectors. And as it stands today, the technology readiness level of 3D concrete printing has reached up to 7. But of course, at technology readiness level of 9, then it becomes commercially competitive. from this graph, you can see that significant amount of publications have been released between 2007 and where we stand today with more than 430 publications, projects, up to 212 and several patents. So this actually shows the global interest in 3D concrete printing around the world. Of course, some barriers still exist, which I believe maybe some of you will want to ask us in the course of our Q&A. And these borders around reinforcement, standardization, and so on. So those are still some challenges that I believe Marchant will be speaking more to that. So a study was recently conducted in Germany where a comparison was made between conventional construction and 3D concrete printing construction. You will see from the graph or on the left-hand side, you will see that transportation is a major concern when it comes to 3D concrete printing. I need to mention that the comparison that was done here was for two-story building, for a two-story building using different construction technique, conventional and 3D concrete printing. The printed structure actually was load-bearing with no steel reinforcement, and then the slab that was used was precast hollow core panels. We can see the significant, you can see the significant difference in terms of cost, but transportation is quite significant. From this report, if I give a material cost estimate for the 3D concrete printing, it was about $259 per cubic meter, and that gave about 440 kilograms of CO2 emissions per cubic meter, in comparison to the conventional concrete, where it was about $68 per meter cube, with 267 to between 267 and 343 kilogram per meter cube. And that actually borders on transportation of materials and also the 3D printing, the 3D printer. So in the light of this, here at Stellenbosch University, our research is looking at using more sustainable materials. With conventional 3D printing, you have significant amount of cement, which some people believe that, oh, that's not sustainable. So our research, we have begun to look at, and we have rolled out a number of publications in this respect, reducing the cement content and water content significantly, using cement extenders such as fly ash, slag, and then metal kaolin. Not only that, we have also increased the aggregate to binder ratio. If you see the graph that you have here between 2018 to where we stand, or last year, 2024, you can see increase in terms of the aggregate to binder ratio. The last three publications here are from Stellenbosch University. Our students, Marcus Colin, actually increased the content of the cement extenders to replace cement up to 60%, which is, I think, still the highest globally at the moment. And we have other students who are replacing our natural aggregates, that is sand, with construction and demolition waste up to 100%. And we've made published some fantastic articles in that respect. So moving on to testing, typically, concrete codes are not only restricted to design models and rules, but of course they refer to standard tests for concrete in terms of the fresh states, hardening properties, or properties in structures, and then some specifications. As you can see, our SANS code definitely adopting the EU code. And typically with our tests, we print a sacrificial sample from which we can core out samples for compression test and then elastic modulus. Sometimes we can print, different sacrificial samples and then take our samples from different directions. As you know, that 3D printing, the material is a layer by layer deposition. So the effect of anisotropy is very, very important. So we take from different direction to look at the influence of the printing direction. Interestingly, we have some international society, RILEM, for example, technical committee, where we have a committee looking at 3D concrete printing to present a report on the first state. I think the committee has been working since 2021. We also have the RILEM technical committee on additive manufacturing. Some of us are privileged, some of our colleagues are privileged to be on that committee. Recently released about 4 articles on different aspects on the mechanical properties of 3D concrete printing. We've got some working groups from the FIB task group um, looking at structures made with digital fabrication, all in an attempt to understand 3D printing, and then eventually we know that standards will be coming out from that. So going forward with printing, we'll see that typically when we print, develop our mixed formulation and print, we would normally check for the buildability. So hardening properties are tested using cylindrical samples, but also buildability up to 1 meter within roughly about an hour. This is a nice print with 50% fly ash and 10% slag. 36 layers was achieved. And then this is 40% of fly ash replacing cement, plus 20% of metakaolin. And then with 60% of slag, it could go up to 77 layers. So, but of course, with 3D printing, as we know, is self-supporting, no form work. So shrinkage is a major concern, as seen in this 3D printed building. I need to emphasize or mention here that the crack width have been colored black for visibility. It's in the actual structure, like the one at the bottom here, you cannot actually see it, but we have colored it for the purpose of visibility. So crack is a major issue because larger surface areas are exposed to the atmosphere. So it is something that we're giving attention, and a number of our students are working on this to determine the shrinkage of 3D printed concrete. Several methods can be used. Digital image correlation can be used to measure the shrinkage of 3D concrete printing. How you measure it is very important. And also, we have our PhD student, Heinrich, who is currently investigating different method of testing it, where you use the stored with your DMEC gauge. But we've discovered that this is not accurate because of inconsistency in holding the test equipment or the measurement equipment. Is also looking at a situation where you apply these plastic holders, and then you connect your LVDT to measure the shrinkage. So in essence, shrinkage is something very important when you deal with concrete printing. And we can investigate that in certain stores, like I mentioned, or in certain, in certain 3D printed hard plastic as shown in these figures. And then we can apply an LVDT to measure the shrinkage over time. Okay, and so that is the current test that is ongoing. And going forward with technical status of shrinkage, a recent publication from Heinrich, who is one of our PhD students, just collated. It's a review article where he shows the performance of 3D concrete printing in printed concrete in terms of shrinkage for different types of, comparing different types of shrinkage, drying shrinkage, plastic shrinkage, and autogenous shrinkage. And you can see that it was compared with cast, okay, cast mixture compared with 3D printable mixes. So, but overall, we feel that the right approach is to use LVDT, that we give accurate measurement of our shrinkage as demonstrated in one of our past studies. Okay, so in terms of properties, mechanical properties, we can see that for this study that was conducted here at Stellenbosch University, where reinforced 3D concrete beam resistance was predicted with reasonable accuracy using the European code EC2 model code that was done by one of our one of our PhD students who is graduated. But in terms of shear resistance prediction overestimates the recorded resistance significantly. So for reinforced frames for low-rise houses, say 1 to 3, shear dominates, okay? Loaded beam reach 50%, 50% of the EC2 design value, which is poor because of the poor bonding. However, when the bonding of the interlayer is improved, performance can also be improved. And then the flexure dominant failure was within 5% of the European code design, the European code. So going forward, these are some of the beams that he tested. And then you can see the way the beam was reinforced. So shear is still a major concern. However, with improvement in the interlayer bonding, as improvement in the performance was achieved. You can see different topological layer that was developed from the nozzle shape and size, and then eventually the shear was satisfied. Just my last slide because of time. On thermal comfort, we have also investigated. This was conducted by a student supervised by Professor Gideon Vassile and Professor De Villiers, using phase change materials from recycled brick aggregate, and the natural aggregate, which was Malmesbury sand, was replaced up to 65%. And exposed to the atmosphere just to see how it responds to the thermal comfort. And then corrosion in terms of durability, this is still ongoing test with corrosion, with chloride-induced corrosion, restraint shrinkage. These are some of the experiments that our students are currently conducting, finite element analysis, reinforcements, and then we are heavily working on circularity. In essence, reducing cement content, replacing our natural aggregates with construction and demolition with, and even multi-generational reuse, where the printed structure is demolished and crushed into fine aggregate and reused in the printing. So these are some of the state of the art in terms of where 3D concrete printing stands at this time. I'm going to hand over now to my colleague, Marchant, who is going to take it further from here. Thank you. Marchant?
Perfect, John. Thank you very much.
Do I go back? Is it fine here?
Yeah, you can go to the next slide. Thank you very much. Thank you very much, John. So for the rest of the presentation, I'd like to double take on a strategy for material supply that we use in industry. I think, as John quite rightly pointed out, there are many aspects related to the supply cost of the raw materials that we use for 3D printing. We look at the sustainability of these raw materials, and very importantly, from a commercial aspect, we of course have to consider the cost of supplying these raw materials. After that, we'll look at some of the design code provisions that have been made available internationally to contextualize 3D construction printing and provide, design guidelines for the industry to follow. And then we'll look at some projects and different ways that these have been designed, regulated, and approved. And then finally, we would take a look at some of the testing that has been conducted to facilitate these approvals. So to kick things off, we look at ready-mix printable concrete. So John, if you could please move to the next slide there. We in the industry, we have kind of three main methods of supplying printable concrete. So For continuous mixing applications, it's typically a mortar, so material with a pretty fine aggregate. As John pointed out, this tends to have a pretty high binder content, binder referencing the cementitious content in this material, which can be split between the cement itself and then the supplementary cementitious materials that are used to replace those, and mineral fillers that can be used, which all build up the powder fraction. But as you see for mortars, we're looking at the range of about 800 to 1,000 kilograms per cubes, no coarse aggregates, and then an admixture package used to facilitate the workability properties that we require. If we look at some of the batch mixing solutions, which are predominantly used in the industry, you could either have a mobile mini batch plant or a ready-mix truck is a solution that we've been using quite extensively in industry to facilitate the scalability of this material supply. So if we look at some typical 3D printable concrete mixtures, you would see that comparing a mortar to a concrete, for example, the C2530 material, we're able to substantially reduce the cement content as well as the cementitious or the supplementary material content. We incorporate a lot more aggregates, and in some of my next slides, I'll show you what the significance of this is, particularly related to the amount of paste required to coat those aggregates and the shrinkage performance of that material. But if we look at concrete versus mortar, we see that by increasing the aggregate content, by reducing the amount of powders, we're able to substantially reduce the cost of this material. From a regulatory perspective, this is also very interesting because once we move from a dry bagged or a pre-blended product, we move to something that the industry understands. So if we look at concrete from a European perspective, it's EN 206 that governs the supply of ready-mix concrete, and in the US context, it's ACI 318. We've been able to substantially reduce the carbon embodiment. So top right of the screen, you can see a typical mortar versus a mortar that has a high cementitious, supplementary cementitious replacement. But then with a concrete material, we're able to reduce that down to about 190 kilograms per cube versus between about 300 and 450, as John had previously mentioned. I'm wearing my commercial hat today, so it's very important to point out that there are capital considerations related to employing concrete versus mortar or sort of continuous mixing system. So the scale and the supply needs to be considered in context of the material that you would be using. So John, if you could please move to the next slide. If we look at ready-mix printable concrete and we look at the regulatory context, as I had previously mentioned, we have industry norms such as ACI 318 and EN 206, which very much supports the design approval process with documented protocols for QC, quality assurance, and quality control. We move from kind of specialist grouts to just target mix specifications, as we typically would for ready-mix concrete. And we also have codified performance and durability requirements that we can reference in these existing codes. From a financial context, we're able to reduce the cost by about 70%. And this is by and large related to the supply chain availability. So ready-mix is a regionally available product where mortars are not. We're able to leverage increased aggregate fractions, and putting this in a financial context, aggregates are much more economical than cementitious powders. So from that perspective, it's a no-brainer to move to ready-mix printable concrete. And then the final aspect is dry bagged or pre-blended mortars require some logistical considerations in the sense that you need to dry these aggregates, so there is cost and energy involved. It also requires pre-blending, and it requires packaging and transportation logistics, as John had pointed out for the previous study that had been conducted. But quite interestingly, from a performance context, we're able to reduce the paste volume fraction for these ready-mix materials, which provides increased dimensional stability. So it allows us to reduce the plastic shrinkage potential of these materials and mitigate these adverse effects of plastic shrinkage cracking. And basically what it boils down to is less paste means we need less water and or additives to get the desired workability properties, which means that we get more strength per dollar and improved sustainability performance. So this is the reason why we in the industry very much prefer to work with a ready-mix printable material. John, if you could please move to the next slide. However, it unfortunately is not just that easy, and we can't just always use ready-mix materials, and we have some specific project considerations or limitations in the sense that when we consider a new project, we have to evaluate the geometry. So what is the size, shape of the specific project, and what is the resolution that is required, bearing in mind the aesthetic considerations. That leads us to then choose a specific material, whether that be a mortar, a batched material, or a ready-mix concrete. And we have to then consider the reinforcement strategies that we would need to provide. So depending on the design codes, and in some contexts, the lack of standardization that accompanies those codes, we have to consider the loading and the performance requirements along with the durability. And this is an interchangeable set of considerations that again influences the material and the reinforcement strategies that we choose. And kind of the collection of these 6 properties that I've covered now all influence the cost of this project. So it's very important to consider your location, your geometry, and the performance of this building to optimize costs to ensure that it is economically viable for us to scale this technology in the construction industry. So John, if you could please move to the next slide. If we can touch on now some of the projects that have been done, we have two types. Either it can be a load-bearing structure where the 3D printed aspect of the structure takes all the load, or it can be non-load bearing where you use an RC frame to take the load. So John, if you can move to the next slide, please. Bearing this in mind, we can now look at some of the codes that are available internationally. So Dubai has a very, they've kind of set the scene by setting through the Dubai municipality in June 2024. They released a guideline for 3D concrete printing for design and construction. And what this has done is it collates various building codes and regulatory frameworks, such as the Dubai Building Code, Decree 24 from 2021, which is specifically regulation for 3D printing in construction, which provides a legal framework, which mandates approvals and registrations to use this technology. But there's also an administrative resolution released in 2023, which specifies the technical and procedural conditions for implementing this technology. And this is really where the structural validation, material specification, and production oversight that we typically see in construction projects are considered and contextualized for this technology. And then finally, the technical standards cover then the compliance for testing, structural inspection or special inspections, as we typically call it, the mixed design, and the on-site execution, which is very important to ensure that the design intent is actually facilitated on the construction site. And it emphasizes, the traditional aspects such as traceability, quality control, conformity, and reinforcement practices that need to be employed. So John, if you could move to the next slide, please. If we look at the US context, there are 3 main codes that have come to light in recent years, which is ICC ES AC 509. So this is an acceptance criteria, very similar to an AGROMA certification that we would understand in South Africa, or QQI, or a BBA certification in the Netherlands. There's then ISO and STM 52939, which is a quality control standard, and I'd say probably the most robust and widely implemented in industry to date. And then a very recent draft standard, which has gone through its 2nd phase of public review, which is ICC 1150, which is more of a performance-based design approach to 3D construction and we see this as taking a very important step forward for the regulation of this technology. So John, if you could move to the next slide, we can go into the specific details of these codes maybe in the Q&A. But I just want to double touch on some of the design examples. So what we've seen in industry is either design assisted by testing, we've seen rational design approaches. So I've got two examples for design assisted by testing. The first is a Nijmegen Bridge, which is a 26-meter topologically optimized bridge executed in 2022. And it comprises of various bridge segments that were printed and then post-tensioned directly on site. It was facilitated by the Technical University of Eindhoven, Wibke and Bos were the structural engineers on this project. St. Gobain, Heever, Baymix, and BAM were the contractors, and it received funding from the Rijkswaterstaat Major Projects and Maintenance. If we look at the design assisted by testing context, we look at the basis for structural design, so Eurocode 0. And then section 4.2 governs the material and product properties that need to be considered. The formative section of 5.2 for design assisted by testing, supported by Annex D, which outlines the prescriptions for design assisted by testing. So how should we actually test and what should we test to confirm the structural design and the appropriateness of the tests conducted? Next slide, please, John. So this was a very innovative project. It was in 2022. So it had to follow a bit of an iterative design approach where the conceptual design was initially facilitated and validated through, on the one hand, structural testing, and on the other hand, printability testing to confirm the parametric design parameters that would be used to optimize the design. This iterative process was followed until the final design was able to be reached. Then from a production perspective, a full-scale manufacturing mock-up, so you can see at the bottom of the screen, this part 3 was produced, and it was then tested to confirm that the structural parameters that need to be considered are actually executed in a real-world scenario. So John, if you then move to the next slide, we can look at how this test was conducted. So you can see this part 3 was executed. Now, due to the support conditions, it was important to establish whether it would be bending or shear dominant, and that would be due to the geometry of the support conditions. There were certain material tests that were conducted, so to confirm the basic mechanical properties of the material, but then also looking at the full-scale structure. And the design had the requirement of between 100 and 115 kilonewton for the loading that was imposed for this third-point bending or four-point bending flexural test. And as we can see that from the in-situ diagnostic tests, they were able to exhibit through the testing phase that 100% of the design ultimate limit state was able to be reached. So the 100 kilonewton in bending was achieved, and then 345 kilonewton shear capacity was shown. And from that, they were able to verify that the design was appropriate, and the project went forward, and it was really a great project. Secondly, if we look at Project Milestone, again in the Netherlands, this project was for a residential context. And as you can see, this building was made out of a series of prefabricated elements. So they were printed off-site and then transported to site and installed. For this project, they selected two wall types, type A and B, as you can see on the top of the screen. And the loading considerations for the two respective tests were centric loading. The requirement was 19 kilonewton, and then an eccentric loading case of 10 kilonewtons in the axial case, and then 3.3 kilonewton on an eccentricity. So John, if you move to the next slide, you can see what the experimental setups looked like. And in this case, they were just loading up to the required design load prescriptions, and they were assessing the permanent displacements. There was no visible damage in either of the tests, and again, the engineers would then have the comfort to employ this technique for the project. So we can move to the next slide. The next one is a project executed by our company, 14 Trees. It was in Kenya, and the client was for UNICEF. This was a cavity wall construction with no additional framing reinforcement, so just the 3D printed leaves linked together with typical wall ties as we'd see for masonry buildings. 2 architectural options were proposed with various load conditions that had to be applied. And what we saw is that the design assumptions were verified through structural testing, and the KENAS accreditation was applied to using this specific technique. We can move to the next slide. And my final slide, which is a project that we did with my former employer in Ireland. And this is one that used a more typical design workflow for the approval process. And it adopted a rational design approach with some companion testing, so no large-scale structural testing. And the reason being that it was a very solid workflow adopted to get this regulated, something that the industry understood. So the EN Eurocode 6, so for the design of masonry structures, was employed. It was coupled with ready-mix printable concrete. So if you remember the previous comments with this facilitating design approvals. So the materials were regulated according to EN 206. And then the building control amended regulations, or BCAR requirements from 2024, according to the Irish building regulations, were adopted. And the quality control followed ISO ASTM's 52939 guidelines, as I covered previously. And then we conducted a series of companion specimens to verify that the material and design parameters were indeed executed correctly. So I think that's a nice overview of the various ways that we can regulate 3D printed construction. And I'd be happy to touch on some of these aspects in the Q&A after. Thank you very much. I'd now like to introduce Wibke, who'd be giving us a bit more of an overview on the national context for the design of 3D printed concrete in construction.
Thanks, Marchant, and hi, everybody. Yeah, so as Marchant mentioned, he's given the international view on regulation of 3D printed concrete. And just to fill you in a bit on what that looks like in the South African context as well. So in our national building regulation, as I'm sure you're aware, SANS 10400, 3D printed concrete obviously wouldn't meet the deemed to satisfy solutions that are set out there. But the standard does, of course, make allowance for rational design or rational assessment, and Marchant has also discussed that process quite a bit. And Agrement certification is always an option. And then since our SANS 10160 is an adaptation of Eurocode 1990, we also have that option of design assisted by testing. Sorry, John, can you just go back one slide? Thanks. We also have that option of design assisted by testing in our SANS 10160. Since ISO has published the quality assurance standard for additive manufacturing and construction, we can reference that as well. So that also gives some basis for that quality control aspect. The downside to all of these, or the hurdles that I think any technical team would experience wanting to implement 3D concrete printing in South Africa, is that any design that is supplemented by testing is extremely time consuming and costly. And the current regulatory options as they're laid out there would all require testing to some degree, and in most instances to quite a large degree. And then in addition to that, whatever testing is performed, or especially if you go the route of Agrement certification, then that certification is very case or project specific, and understandably it's the certification is then also just limited to the scope and the specifications under which that testing took place. And so overall, for the large scale and successful uptake of 3D printed concrete as a technology, we do need to develop 3D concrete printing specific standards for us in the South African context as well. And so the question then is, how do we go about doing this? Next slide, please, John. And so what we, and by we, I mean the 3D concrete printing research team here at Stellenbosch University, what we believe would be the most sensible or practical option to move towards standardized 3D concrete printing in South Africa would be to include a chapter on additional rules for 3D concrete printing in our new concrete structural design standard. And just to provide a little bit of context around that, as you'll be aware, the new South African Concrete Design Code, SANS 51992, was published earlier this year together with its national annex. And this is a straight adoption of the Europe Code, Concrete Design Standard 1992. And so with our new concrete design standard, there are several chapters included there that cater for other concrete types, such as precast concrete or plain and lightly reinforced concrete. And these chapters are then quite streamlined in that they only contain additional rules to cover the aspects of these other concrete types that are different to conventional concrete characteristics or aspects. And so what that then means is that this new concrete code that we have gives us the framework to include 3D printed concrete in a standardized manner by adding a chapter that includes the rules and requirements that need to be taken into consideration for 3D concrete printing, and specifically then only those that are different to conventional concrete. It took many years to develop the new concrete code by, amongst others, Profs Jan Wiem and Gideon van Zyl and Chris Roth, and I'm definitely forgetting some names there. And normally it would be many years before a revision or a change to such a standard would even be considered. John, if you could just click on to the next portion. Thank you. But because the basis of our new concrete code was the first generation Euro code, which originally came out in 2004, in Europe, the second generation of Euro code or concrete code has already been published. And so therefore, there are already talks underway in South Africa for the revision of our just published concrete code to align it to the second generation Euro code. Which means, happily for us, that this not too distant revision would therefore present an opportunity to include a chapter on additional rules for 3D printed concrete. Yeah, if you could just go one back, thanks. Yes. And so such a chapter isn't developed overnight though, and one of our PhD students, part of the team, is busy working on what such a chapter would then include. This includes identifying and defining the divergences between 3D printed concrete and conventional concrete, calibrating material partial factors for 3D printed concrete, mainly based on a large RILEM test data set. And then also developing 3D printed concrete probabilistic models for flexure and shear, because these look quite different in 3D PC due to the anisotropy and the weak bond strength. And then also determining what the considerations would need to be for reinforcement and durability. So yeah, John, you can click on so long. Thank you. Those are kind of the developments on the regulatory front in South Africa. But another important aspect that needs addressing to facilitate the uptake of 3D printing concrete in South Africa is integrating the whole design and manufacturing process into our existing conventional construction processes. And so another of our PhD students, Kim Tim, has made this her task. She started with the widely used Heever plan of works, which breaks down the conventional construction processes into typical stages. And then based on surveys and interviews with off-site construction contractors and 3D PC specialists. She identified critical elements or roles that need to be included for 3D CP to be incorporated in conventional construction processes more seamlessly. John, if you could click on, please. And so then some of these key aspects that Kim identified that need to be included are that BIM integration is absolutely essential to the process, given the digital nature of 3D concrete printing. A 3D CP specialist or engineer must also be involved, preferably early on from the inception stage to advise on feasibility and right through to manufacturing or construction stages. A 3D CP handbook should also be developed as a quick reference for design teams, similar in principle to the FIB precast handbook, which I'm sure many of you are familiar with. And also a digital certificate of compliance must form part of the documentation process, which captures important printing information from printing speed to weather conditions and so on, so that documentation can then flow back to the structural engineer or the regulatory authority that is involved. So those are just some of the aspects that she's identified that need to be developed to facilitate the inclusion of 3D printed concrete. One of the important ones, obviously, being the specialist or 3D concrete printing engineer. John, if you could click on. And we here, the team at Stellenbosch University has been very busy producing such specialist 3D concrete printers over the last few years. 10 PhD graduates specializing in 3D CP have already completed and are out there in the world working in different capacities. And there are about another 10 PhDs currently in the pipeline, also actively working on different aspects of 3D printed concrete. So there's a lot of knowledge and experience being built up for our local South African 3D concrete printing industry as well. And then finally, John, if you could go to the next slide. Another important aspect is also knowledge dissemination. And so, unfortunately, workshops are still, to some degree, quite limited. There have been a number in Melbourne, Australia, and then over the last 3 years, a summer school in Naples, Italy has also been presented, regularly supported by RILEM and FIB, where some of our team members have also been very actively involved. And what we're tentatively planning towards over the next few years is also a series of workshops here at Stellenbosch University to help equip and upskill the local 3D PC specialists so that we can move forward in those aspects as well. So I think that's it from our side. Just managed to squeak it in time. We haven't left very much time at all for questions, but if there are any burning ones, we're welcome to address those.
Thank you very much, John, Marchant, and Wibke. If you can join me and react and give a thumbs up if you agree that was a good presentation, then the top is a react button, or thumbs up, or whatever, hands, anything. Thank you. Yes, it's silent, but it's appreciation. Thank you very much. Thank you for your time, your presentation. Very good presentation. I really appreciate that. All right, we've got time for a few questions. I think we can't let this presentation go without any questions. If you have a question, please raise your hand by using the raise function at the top. I see John Roberts raised his hand, but I think he might have clicked it by mistake. I don't know if you still have a question, John. But otherwise, any other questions? There's a question in the chat. Let me just get to my chat. The innate BRC seems to be not allow rational design more recently. Any comments on this?
Yeah, John, you're welcome to jump in. So I personally have not, I do not have experience with submitting a rational design to the NHBRC, but yes, it is more tricky. It's just from their perspective, it is far easier if you just present them with the Agrement certificate, for example. So I want to say, legislatively speaking, the option is there, and it is catered for. Whether the NHBRC then specifically is happy to give its stamp of approval on that, I can't comment too much on that.
All right, thank you, Wibke. Is there any other questions? While people are thinking or typing a question, I maybe have a question. It's, I think, a question that you guys will receive quite often, and you probably got a standard answer for it. 3D printing seems to work very well in a country where you've got high labor costs and highly skilled labor. What do you see the advantages of 3D printing in local economy like South Africa, where labor is in general not as advanced or experienced or trained, and also it's much cheaper labor compared to other countries?
Maybe I can comment on that. Yeah, it's always the question, and then Wibke, you can, of course, comment thereafter. Of course, like you mentioned, is the question that we always receive about 3D concrete printing, that is going to lay off workers and all of that. But there's a recent study actually that shows that you almost need the same number of people, with conventional practice construction. The only difference with 3D printing is that you need to train them. So I believe people can be trained. You do minimal training and then they can be put on the job. So, but like I said, there's a recent publication that you almost need the same number of people. Marchant maybe can comment on that.
John, I think from our perspective, we certainly see the value being driven if we have more engineering or topology optimized structures where we're looking to leverage design efficiencies through the freeform capabilities of this technology. So not to, in all contexts, try and compete with, say, traditional low cost applications exclusively, because you raise a very current topic about the maturity of the labor market and the cost of the labor associated in that market. But we really do see when it's more engineering driven solutions where we're looking to evoke efficiency in terms of the geometry that we create, that we would see potential for this technology in any labor market.
Wibke, you wanted to add or not?
I think what's certainly there is some upskilling that is required if you're shifting to a different technology. But I think another significant advantage is the scale at which, whether it's low-income housing or whatever the structure type is, the scale at which that can then be produced. And given the shortages that we have in our country, you could use the same amount of people to produce a far greater product at the end of the day.
All right, thank you. There was a question up. There's a question, Ralph Hassan. You can speak up.
Hi. Yeah, thank you for the presentations. I think my question will basically go to John Babafemi. He mentioned the use of recycled fine aggregates to replace natural aggregates. And well, in the context of Africa, I don't know, some of the questions I get personally is that how much of the recycled fine aggregates or construction and demolition waste do we even have in Africa to consider it as an alternative to the natural aggregates?
Yeah, thank you very much for your question, Ralph. I think recently I think it was last year, where we published the paper. We took an inventory of available waste in South Africa. that have the potential to be used. So, but specifically with construction and demolition waste, our finding is that we do not have sufficient to totally replace natural aggregate in 3D concrete printing. But with most international codes, you will see that the limits, maybe with conventional concrete now, limits replacement up to 25%. So, but we're investigating full replacement, like I mentioned, from 25 on to 100, up to 100%. But where it is not sufficiently available, then you can replace up to 25%. And some interesting results that we have is that even at replacement, of course, this is a function of the type of construction and demolition waste you're using. But for the one that we tested, okay, which we got from CDEL, at 25% replacement, it actually outperformed the control. Yeah.
Thank
So
you
it's
very
going to
much.
depend on availability. Yeah.
Okay. Are there any other questions? There's a question in the chat. We can just read it. Thank you very much for this impactful lecture. My question is, is 3D printing applicable to buildings up to 6 to 7 floors and use lightweight materials for the cladding to reduce the load? Is there a possibility to build a 6 to 7 story building if you make all the cladding and all the features light?
I think Marchant can comment on that. Yeah.
I think if we consider prefabrication, so producing elements off-site, installing them, there is an opportunity to replace your wall system with 3D, as a cladding element specifically. If we're looking at in situ construction at this stage of the technology's development cycle, there are not machines that can go to 6, 7 stories. I would also challenge the economic viability in the sense that you would have to create very massive frames to facilitate this type of construction. So my feedback would be prefabrication. It would be worth at least digging into the numbers and assessing the economic and project feasibility. But for on-site or in situ construction, I would have my doubts at this point in time. Yeah.
All right, I think that concludes our session because our time is running out. It's already 4:10, but most of you, almost all of you, are still here. Anyway, thank you very much. Thank you for 3 presenters. Thank you. It was an excellent presentation. A lot of questions and a lot of unanswered questions still remains. And I'm looking forward to listening to this presentation again in 2 years' time and to see where we are then. So thank you very much. Everybody have a wonderful afternoon. It's almost the end of the day. You can probably go home now. Yeah, I will see you at the next concrete class, and you'll see the invite on LinkedIn or on email. If we can just ask the presenters to stay behind, and then we see you all at the later stage. Bye-bye.